Hello, Science 30s. I wanted to spend a minute on talking about section 1.1 on electric, or basically on field lines. We're going to talk about three different kinds of fields, and shortly we'll learn some formulas for those. Um, so the first one is, or all of these fields are called action at a distance um, fields, or basically the forces that exist in these fields act at a distance. So there's no direct contact between any masses. And when we talk about a field, that's just like you imagine a field, an area or a region. But it's an area or region where you would feel an influence from from something, okay, either electricity or magnetism or gravity. So that's sort of the general idea of fields. So we're going to look at electricity first. The famous example is a man named Thales, and he was a Greek. He was rubbing amber and noticing that it attracted dust and paper. The word for amber is electron, and that becomes the root for the word electricity. So it's kind of cool that that's where it comes from. If you've ever seen amber, it's fossilized tree sap. It's sort of a yellowish looking rock. Um, anyway, there are two types of electricity. There's stationary electricity, which we call static electricity, and that's actually the beginning of understanding how electricity works, because um, when you build up charge, you're building up a number of electrons. So if you remember from your studies in science, an atom is made up of protons, electrons, and neutrons. And the buildup of electrons is more negative charge. The simple understanding for electricity is the law of charges. Like charges repel, so two negative charges will repel each other, or two positive charges would repel each other. And then vice versa, opposites attract. So we'll see that play out in our understanding of fields. So uh, it's worth mentioning here just a little bit about lightning. Lightning is static electricity. Effectively, what happens up here in the cloud is you get uh, basically water droplets, and actually some of it turns into ice. And as they bump into each other and are kind of churning inside the cloud, they exchange electrons. And one of the ways to charge something is just to rub it. So, you rub a balloon on your head um, or on your hair, and it'll stick to something. Your socks in the dryer rub against each other. So the contact causes static electricity. The positive charges tend to migrate to the top of the cloud, and the negative charges tend to migrate to the bottom of the cloud. And what happens is then these negative charges exert repulsion on the negative charges in the ground. So they get pushed deeper into the ground, leaving the positive charges behind. Essentially, the positive charges don't ever move. I don't know if that's really going to be an issue in terms of what we'll look at, but just know the electrons are the ones that really, for the most part, move. So what happens then is, as the charge builds up in both places, the cloud will send down what are called step leaders. And these kind of branch and split on their way down. And as they get close to the ground, it's kind of like the ground becomes aware that there's a negative charge that's on its way down, and it starts to produce what are called positive streamers. And those positive streamers uh, make their way up towards the negative step leader that's coming down. And when they connect, then you get this pathway for the electrons to take towards the positively charged surfaces of the Earth, and then they take it. So it all happens in incredibly short amounts of time. But what's at play here are uh, the attraction and repulsion of like and unlike charges. That's what's going on here. You need to know that the amount of charge is measured in coulombs. It's named after Charles Coulomb. In French, you'd say Coulomb. And that is the capital letter C. And you'll see that in a lot of the formulas that we're going to look at a bit later. Capital C is the unit of charge, and it's in coulombs. 1 coulomb of charge is a huge number of electrons, 6.25 times 10 to the 18th. That's a billion electrons. It's a huge amount. And you could, if it helps you, a coulomb of charge is basically how many electrons might be in a lightning strike. It's pretty hard to measure, but so it's a huge amount of charge. Just so you know, a proton and electron have a really small amount of electrical charge on them. These numbers are not, I've not seen them on your data sheet, but just know that most objects, if you rub a balloon on your hair or whatever, the amount of charge that it has will be really small. Usually in the micro coulombs or sometimes even nano coulombs. And so, but just to show you how small of a charge in coulombs an electron and a proton have, I added those two numbers right there, 1.6 times 10 to the negative 19. Okay, so what's worth reminding you about again are different kinds of materials, because you'll see this come into play as we look at electric fields. There's a range of materials. They start with insulators, if you remember those. Insulators actually resist the flow of electrons. Current doesn't flow very well through them. They can hold a charge, but that charge doesn't distribute all the way around the object. It kind of stays restricted in a certain spot. That's why if you rub a balloon on your hair, only the side of the balloon that you rubbed will stick to the wall, not the side where your hand is or anything like that. So semiconductors are cool. They're kind of in the middle. They're in between insulators and conductors. If you remember from chemistry, the metalloids make those up. It's the staircase between the metals and nonmetals. And also that mirrors the fact that they can act like insulators or conductors depending on usually their temperature. But conductors, these are the materials that allow electrons to flow really easily, and they're all metals, basically. Every metal is a little bit different in terms of how well it can conduct. And then under ideal conditions, you can get superconductors. So they have almost no resistance at all. Current can flow extremely easily, unimpeded. They tend to be super cooled, though. They have to be cold in order for that to happen. I'm going to remind you about this in your data booklet. It's most of the information we're going to be learning is on pages 2 and 3. I'm just showing you mine here, but and I've written a bunch of stuff on mine. So on these in here, there is actually a section that has these prefixes, and actually that's even before that. That's actually on the very first page. So in here, there's a nice table, and I copied that obviously here into your notes. If you ever see a prefix, so a number in front of a unit, and they're all listed right here, you don't need to have them memorized. Just know that you have a reference table and you can look them up. What we're going to see right away is this one right here. This is the Greek letter mu. It's kind of a U with a tail on the front, and it represents micro. So micro means times 10 to the negative 6, okay? And we really could, it's actually a common one when we're dealing with charge, because electrical charge is measured in typically really small amounts. So what we should know about electric charge is that the total amount of charge needs to stay the same if you are generating it, okay? Oops, sorry to cover that up. So if you rub two objects together, the amount of charge that one object picks up has to equal the amount of charge that the other one lost. So we are not losing or gaining any total charge, if that makes sense. So I'll just quickly go through this example. If you're wearing socks on the trampoline and you acquire a charge of negative 55 microcoulombs, what would the charge now be on the trampoline? So if you've initially, both of you have to assume that both you and the trampoline would be neutral, but then in the process of rubbing, that energy causes electrons to jump from the trampoline to your socks. So the trampoline should now have a charge of positive 55 microcoulombs. Okay, it would have lost electrons and your socks would have gained them. If, and again, this number is not a number you're going to have to memorize, but it wouldn't hurt to make note of it somewhere, even on your data sheet. 1 coulomb is equal to 6.25 times 10 to the negative 8, or 10 to the 18th electrons. It says, then how many electrons did you gain? So the way I like to tackle these is to just do a simple conversion. You might want to set up a ratio if that helps you. But really, we have 55 microcoulombs, and we need to convert that into electrons. So what we do is we just set up a simple conversion fraction where we can say that in 1 coulomb of charge, there are 6.25 times 10 to the 18th coulomb, or 18th electrons. Now I'm using the E button, and I'm going to emphasize that a bit later. If you're using a TI-83 calculator or 84, you have to hit Shift, and then it's the EE button, which is, I think it's the comma above the 7 on your calculator. Using this number is really slick, or using this key is slick, because E stands for times 10 to some power. And your calculator will know that's what you're doing. That way you don't have to go 6.25 times 10 to the hat, or to the power of, negative 6 or something like that. And so I'll emphasize that a bit later, but when you see me write E, that's what I'm doing. Now, we have one problem here with this conversion, and that is that 55 microcoulombs is really going to be 55 times 10. So I'm going to use that E again, E to the negative 6 coulombs. Okay, so because I know I kind of wrote that backwards, maybe I'll just switch that out so you can see what I really mean by that, because we need to get coulombs in the numerator. So I would change that to a negative 6 coulombs. Okay, so 55 microcoulombs would be like 55 times 10 to the negative 6. Now the coulombs will cancel, and I can just go 55 times e to the negative 6 times 6.25 e to the 18th, okay? And then that will give me my answer. So in this case, I'm going to get 3.4 times 10 to the 14th electrons. Okay, now that's not really a practical calculation. Not you're going to sit there and count electrons, but the idea is that you could determine how many electrons you have. Okay, now this leads us to the second measurement that we're going to look at in electricity, and that is voltage. Voltage has another name. Sometimes we call it electric potential difference, or just V is the symbol for volts. You remember that from Science 9. And what it is, it's the change in electrical potential energy per unit of charge. That may not make sense just yet, but electrical potential energy, that is delta E, or change in energy, and it's measured in units of joules, if you've learned that from other classes. So the best way I can think of to explain this is to just show you what voltage actually is. If we have a strong positively charged Q, we'll just label that charge Q, and then you have a small negative charge, okay, then yellow. Due to the law of attraction, they want to be close to each other. So if you take this yellow sphere, and I guess we could keep that yellow, and if we move it over here, okay, so to do that, I'm going to have to do some work, because I have to overcome the attraction between the two. So as I move it over here, I have to do work to get it to position B. What we say in physics is the work that you do now, that's putting energy into the object. Work is really a transfer of energy from one object to another. And in a sense, you'd be transferring energy into this yellow charge Q, because you have to do work to get it to position B. So if you get it to that point, now it has what we call electric potential energy. Okay. And obviously, if you let it go of it, it could come flying back to the positive charge, and in that sense, it would go from electrical potential energy to the energy of movement, which would be kinetic energy. But the work done is going to equal the force that you exert times the distance that you exert it over. So the further you move it, the more work you have to do, and then the more energy it would then have. Okay, so that's what in this box here highlights. It says to calculate the stored energy, you would use the work formula. We learned that way back in Science 10. I know it's been a long time that you've maybe seen that one. And that actually lets us, oh, actually that is on your formula sheet too. If you look here in your data table, the formula for work is there. Really, if you get into any formulas in this physics section, I would look heavily at your formulas for on page 2 and 3, because chances are it's going to be there. So like we said, the amount of work done to move the charge will be in the charge as stored electrical potential energy. So this definition is really good. The amount of energy stored per unit of charge is defined as the voltage. So there it is in this formula here. Now this formula is not in your data table for some reason. I thought it really should be, because I think you have to use it a few times. So I wouldn't be afraid to add that. You can just write it right in your data book. That voltage V is equal to the change in electrical potential energy per unit of charge. And think of it as just as energy stored per charge. As it notes there, and those are the units for a volt. A volt is 1 joule per coulomb. Okay, coulomb, of course, measuring charge. And sorry that that didn't copy very well. That's supposed to be a capital C. 1 volt is 1 joule per coulomb. So voltage is actually connected to two other measures of electricity, and that is current and resistance. Okay, so we have voltage, we have current and resistance. You might remember this from Science 9. I'll just quickly mention this because I have it drawn here. Current is the measure of how many coulombs of charge flow past a point in a wire per second. So an amp is what we measure current in. Amps are coulombs per second. Okay. Now resistance is the symbol for resistance is R, and resistance, you just need to know that resistance is measured in ohms. And the symbol for ohms is the Greek letter omega. I tried to sketch it there and horribly. But that will come up shortly, because we are going to look at electrical circuits. So the formula for that, the voltage is equal to current times resistance, and it's just a 3-variable relationship. You can flip that around to solve for current or resistance. So, but what I wanted to quickly sketch here was if this cell here, we'll say that this top part's negative and the bottom part's positive. We could just flip it either way, it doesn't matter. If we had a simple circuit here where a wire came out and it went through a light bulb and then into the positive terminal. If this was our simple circuit, what happens is electrons physically flow from the negative to the positive terminal. And maybe I'll do the electrons, let's do those in purple just for fun. So we'll say that each dot here actually represents a coulomb of charge. So 6.25 times 10 to the negative 18. Okay, so a huge number of electrons. But if we could measure how many of these electrons were moving past a point in the wire, we could determine the amps. But as these electrons move from the negative to the positive, they also have energy. And so I like to show energy in this kind of analogy as a amount, or as a kind of an amount of, let's see if I can get this to draw here. Maybe I'll just keep it a little smaller. So each charge has an amount of energy. And so I'm going to show that as kind of, a layer of red on these charges. So when these charges first come out, they have lots of energy, okay, as they come off the negative terminal. By the time, and they basically don't lose any until they get to the light bulb. When they get to the light bulb, some of that energy gets released as light and heat, okay? And then as the electrons go forward from that point, they effectively have lost their energy. So by the time they get to the positive terminal, by the time they get to this location, they've basically lost their energy. And as best as I understand it for electricity, we're not burning electrons. We're actually using the energy that the electrons possess. So they start out with high energy at the negative terminal, and then they lose that energy. It's converted from electrical energy into heat or light or movement if it's a motor, which we're going to look at a motor as well. And then by the time it gets to the positive terminal, it will have lost energy. Voltage is the measure of the potential difference in energy between 2 points. And as we look later at a voltmeter, we could stick one probe right here and then another probe right here and measure the volts using a voltmeter, okay? Measure the voltage across those, comparing those two positions in the circuit. And so just for sake of an example, what we could say is here, we could say that each coulomb of charge has 9 joules of energy. So we could say there's 9 joules per coulomb at position at the negative terminal. And then by the time we get all the way to the positive terminal, we could say that it has 0 joules per coulomb. Okay, so we say all of that energy is gone. It's been dissipated as heat, or definitely the majority of it's been used up by the light bulb. So what we can say then is the change in energy, and sorry I'm kind of writing this everywhere, but the change in energy will be 9 joules. And then the voltage per coulomb would be 9 joules per coulomb. The change in energy is 9 per coulomb. And so 9 joules per coulomb is 9 volts. So this cell or battery, whatever it is, would have a voltage of 9. And we're familiar with a 9-volt battery or a 9-volt cell. Usually they're batteries. So eventually we are going to use this voltage equals current times resistance formula and manipulate it. But I want you to start thinking about how voltage is connected to current and resistance. Okay. All right. So in terms of using the voltage formula, example problem 1.2 and 1.3 are good examples of that. And as you look through these, I'll just highlight them quickly because the work's already done for you. If you're reading a question and you see 0.25 joules of work, or 0.2, anytime you see joules, that is energy or work. Work is actually equal to the change in energy. So these guys are, they're first cousins. They're easily related, because if you do work on an object, that means the object now has energy. So if you see work or energy, same thing. Here's that 55 microcoulombs of charge. Again, they just happen to use that same number, but this is charge in coulombs. So if you want to determine your voltage, you just take the energy and you divide it by the charge. Now you do have to make sure that you get the charge in into coulombs. You can't use microcoulombs. You should use coulombs because a volt is a joule per coulomb. So you can see that they did that here. They turned that into 10 to the negative 6, and then they came up in this case with a voltage of 4.5 times 10 to the third, or 4,500 volts. Okay, which sounds like a big number, but you can have pretty high voltages, and they're not really that risky. But you should always respect electricity anyway. So yeah, the second one here, or this 1.3, if you have it, again, the question shows you that you have 120 volts, and it says there's 15 coulombs of charge per second. So that's actually 15 amps. That's actually current. But anyway, in this case, though, it says how much energy would you experience. So here, we just have to solve for energy. And so you would just multiply both sides by Q. I think most of you guys are comfortable with the 3-variable formula. And there she is right there. So we can take the voltage times the coulombs, and we get 1.8. In this case, they opted to go to kilojoules because that basically would have been 1,800 joules. Okay, which was also a correct answer, but just be prepared for the prefixes that are also in your formula sheet. Okay, so that leaves us to the third point, which is the field lines, and this is kind of the fun one. Field lines are drawn to help you understand what the electric field is like, or this region around a charge. So there's a pretty simple rule for drawing electric field lines, and you depict them using arrows. But those arrows always point in this. It's the direction a positively charged particle would move if it was placed in the field. So as you can see here, if we have a positive source and a negative source, with the positive source, the field lines are moving away from the positive source because that's the direction a positively charged particle would move. Sometimes we call those a test charge. A test charge. You can take a little positive test charge. Sorry, that's not big enough to really tell. Take a positive test charge and just put it near the charge that you're trying to test, and then just see what it does. Okay, and that's the convention. So just the reverse happens for a negative source. The field lines are pointing in, and you'll notice that closer to the negative source, the field lines are actually closer together. Okay, they're kind of starting to bunch up, like the spokes. I always say that, like the spokes coming into the hub of a bike tire. But that means that the electric field is stronger nearer or closer to the source. And that probably makes sense too. And you'll see that as we move on. So here's another little more complex one, which is a little bit why you're safer kind of in a lower ditch in a lightning storm than you are on the top of a mountain or something, because the field lines, they again go from they go away from the positive and towards the negative. So in this case, they're all pointing up. But due to the shape of the Earth, points actually have a higher concentration of field lines. So we can see that right here, and you can also see it right here, that the field lines are kind of bunched up and closer together due to the shape of the ground that is positively charged. That also gets reinforced down here. I just threw some other pictures. But yeah, if you have a pointed object and it's negatively charged, okay, in this case, the negative charges try and get as far apart as they can because of repulsion, but because it's pointed, there's a tendency for the proximity of these negative charges to be a little closer together at the point than they are along the long edges of the point, if that makes sense. So that means, though, then the field lines are more concentrated at the point, and that's basically, or that's kind of why a lightning rod does what it does, is because it actually tends to draw lightning towards the lightning rod instead of hitting something else. and then that lightning rod's connected to a thick cable that would carry that lightning strike safely into the ground and avoid, all of the electrical circuits and pathways that are in a building, for example. Okay. So just to note here, this is showing positive and negative charges. And these dotted lines don't really show the direction, but we can add that. Because in the first one here, these blue negative charges, the field line should be pointing, oh, whoops, I did that backwards. The field line should be pointing towards the negative charge, because a positive test charge would move towards the negative charge like this. And actually, there would be a spot here right in the middle where if you put a charge right there, a positive test charge, it could be equally pulled to both charges, and we would call that electrostatic equilibrium. Not that you need to know that necessarily, but that's definitely a possibility here. And then, of course, this one here shows positive and negative. So the field lines would go away from the positive towards the negative. Okay, so we would draw these with a little arrow pointing at the negative every time. Okay. One other really interesting application is a parallel plate situation. This is where we actually can create a uniform electric field. So where the electric field is the same strength everywhere between the plates. The reason that happens is because in between the plates, as you can see in this depiction, the very first one, right in here, the field lines are all drawn parallel, because the amount, and I'll just clear that out actually because it looks better without my sketch. The area in between the plates actually is a uniform electric field. So we get that easily by charging one plate negative and the other plate positive, like that shows here, and this other one shows it as well, positive to negative. So uniform electric field is really useful. We can actually use that to help us understand the nature of other charges. So that's basically it for electric fields. I'll just highlight quick magnetic fields. I did post a video that's really good on explaining magnets. Magnetic fields originate from poles. Magnets have a north pole and a south pole. You might remember that from your other science classes. And they create interesting magnetic fields, which can be probed by placing a compass needle in the field. So that's what this shows over here. If you take a compass needle, the north part of the red part of a compass needle actually points towards a south pole. And that's what's a little bit trippy when you think of just compass needles. You say, oh, the compass needle always points north. Well, it points geographic north, but in the Earth itself generates its own magnetic field. And at the geographic North Pole, that's actually a magnetic South Pole. Okay, so as long as you keep those straight. But that's why the compass needle, as you can see here, the red is pointing towards the South Pole. Okay, but you do need to know generally that the field lines for a magnet, they go away from the North Pole and towards the South Pole. So, and they tend to come out from the North Pole like this, and then they kind of circle all the way around, as this shows, and come into the South Pole. So, and that's easily mapped by using a small compass needle. You could just place that compass needle. You could put it here, you could put it here, you could put it here, put it here, put it here, and it will point in the direction of these field lines. Okay, so and yes, just like the electric fields, the magnetic fields get stronger as you get closer to the poles. Look how concentrated the field lines are right there, and also how concentrated they are right there. Those are the two strongest regions or areas of influence on a magnet. The last one is gravity, the last field. So gravity is potentially maybe the easier one, because gravity is just attractive only. I guess I didn't add that. It's attractive, or it's attraction only. Okay, so there's no repulsion with gravity. Electrostatics, you have positive and negative. So if you have two positives, they repel, opposites attract. Same with magnets. You can have two north poles, they repel, but a north and a south pole attract. With gravity, with masses, there's only attraction. So We define that, or the direction of a gravitational field. It's the direction a small test mass would move due to attraction if that test mass was placed in the field. And so um, uh, the picture here of the Earth shows those magnetic field lines. I know it's a bit small, but they're all pointing towards the center of the Earth. So shortly we will learn formulas for electric and gravitational fields that you will need to use in your calculations.